Okay, so I guess without further ado, let me first introduce our speaker. Um, so Andrea Martin, right? So we are glad to have him as our speaker today. So Andrea is currently a research scientist at Unbabel. Right? So Unbabel is a company that's specialized in machine translation uh, of customer service, I think communication. Is that correct? Yes. Okay. Um, yeah, he received a PhD in 2012, I think, from Carnegie Mellon University, and then basically later he has published a lot of paper in conference and journal specializing in natural language processing, well, including ACL. I don't know if anyone here know ACL. So ACL is an annual meeting of the Association for Computational Linguistics. So that's one of the top tier conference for NLP. Um, so for the next 2 days, I think he will walk us through the world of NLP. And I think this is a very important topic, especially in Thailand as well, because Thai language has very sort of unique test to NLP. So it's not like English or any other languages. So I hope that what you learn today will be used, hopefully, to develop or use for Thai language as well. So let welcome André.
Okay, good morning everyone, and thanks for the introduction. So yeah, today I'm going to talk about natural language processing. This will be the first of 3 lectures. And so these lectures, the slides. So I sent the slides to Vitavat if we so that they are is probably about to send them. Yeah, so the lectures today and tomorrow are going to be about these 2 topics: machine learning, which is the topic of this school, where the goal is to make computers be able to learn from data, to improve with experience, and natural language processing, where the goal is to make computers process and understand, communicate with us in our language. So just a brief overview about how NLP has evolved over time. So in the old times, before the mid-90s, the dominating paradigm was basically rule-based systems. So this means that if you want to, for example, build a grammar to parse Thai, someone needs to write a lot of rules, accounting for all the different phenomena that exist in language. And of course it could not account for all phenomena because there's language is complicated, it's complex, but it requires a lot of maintenance. It lacks coverage and so on. So in the mid 90s there was something a paradigm shift, so-called the empirical revolution, which basically where people started to use statistical methods, probabilistic methods, for example, building tree banks for the case of parsing, but building corpora, and trying to collect statistics from that corpora and developing models that are able to learn from that data. And this was associated with models like either Markov models, probabilistic context-free grammars. I'm going to cover some of these here today. So these models are very powerful. They as the data, as the size of data increases, the performance of these methods becomes better and better. However, they tend to make very strong independence assumptions, so they are limited in some ways. In the 2000s, there was a new generation of methods based on structured prediction, where instead of estimating probabilities directly, practitioners developed features that were, good cues about what we want to capture in language, and then develop methods, linear models, linear classifiers that are able to assign a weight to each of these features and make decisions based on combinations of weights and features. And this is what underlies things like conditional random fields, structured SVMs, and so on. And this is what I'm going to cover this morning. So then there was another paradigm shift in the last 4 or 5 years, the so-called deep learning tsunami, as Chris Manning puts it, where people started to reuse or look again at neural networks that have that were much older than just the last 4 or 5 years, but became very popular to solve some of the big problems that existed in NLP. So I'm going to cover deep learning methods tomorrow in the 2 lectures tomorrow. So here's the program for these 3 lectures. So today I'm going to talk about linear models and structure prediction. I'm going to talk about Markov models, hidden Markov models, CRFs, and so on. Tomorrow I'm going to talk about neural networks for an NLP, namely neural language models and taggers, things like recurrent neural networks, LSTMs, and so on. And then in the last lecture, in the afternoon tomorrow, I'm going to talk about sequence-to-sequence models, machine translation. I'm going to cover attention, transformers, and some of the recent models that you might have heard of, like BERT, GPT-2, and so on. Okay, so let's start with structure prediction. So structure prediction is a framework in machine learning where the goal is to make predictions that involve output variables that are highly structured, constrained, and interdependent. So it can be used not only for NLP, but for many problems in vision, computational biology, and so on. But it's particularly suited to NLP because in NLP we often need to deal with structured textual data and ambiguous data. And so this happens, for example, in tasks like machine translation, speech recognition, parsing, information extraction, and so on. So let me show you some examples. So machine translation is a classic structure prediction problem. Here the goal is to translate a source sentence in one language into a target sentence in target language. So, for example, here I have an example from Thai to English. Hopefully this example is correct. I use Google Translate. So if it's not, let me know. So we have this sentence in Thai. And the goal is to have a system that is able to produce this sentence Y in English. And we want to do this automatically, right? So you want to learn a model like this by looking at a bunch of parallel sentences, and you want the model to learn how it can translate new sentences that it never seen before. And the translation process involves generating a sentence, an English sentence, which is a very structured object, So we are generating sentences. There is a strong relation between words in that sentence. So this falls into the paradigm of structure prediction. Here's another example, parsing. So in this case, constituent parsing. The goal is to take a sentence, for example, an English sentence like this. Logic plays a minimal role here. And the goal is to decompose this sentence into phrase structures. So for example, we want to say that this is not very visible here. Oh, sorry. No, I was using the laser pointer, but it's not very effective. Okay, anyway, so we have a sentence node here. This sentence node has a noun phrase, a verb phrase. The noun phrase spans the word logic. The verb phrase decomposes it to a verb, another noun phrase for a minimal rule, and an adverb, and so on and so forth. So recursively, we are building phrases, and these phrases are kind of what forms the sentence that you want to express. So this captures the syntax of this sentence, and there is an underlying grammar that I'm showing on the left side that contains all the grammar rules that we can use to parse sentences in English. And so in practice, we extract these rules and weights for these rules by looking at the tree bank, of which a famous example is the Penn tree bank. I don't know, is this completely new to you? How many of you have heard of the Penn tree bank before? Very few. Okay, so this is a very popular. You can regard this, if you don't care so much about parsing, you can regard this as a data set for parsing that has been developed for English. And there are other tree banks like this for many other languages. So a more popular framework, or like equally popular framework, like a different grammar for syntax is called dependency parsing, where we also want to represent the syntactic structure of a sentence, but instead of decomposing the sentence into phrases, what we do is to directly draw these arcs connecting words themselves. And what this means is, for example, for the same sentence, plays is the main predicate of the sentence, and this verb has a subject, which is the word logic. It has an object, which is role. Then minimal is an adjective that is modifying role, and so on and so forth. And we can build a tree called the dependency tree that expresses all these syntactic relationships between the words. And so there's a lot of work that is being done in the last decades on building models for dependency parsing. And as in the previous case, there's also a lot of tree banks for many languages. So there is a very famous project called Universal Dependencies Tree Bank that contains dependencies tree banks for hundreds of languages in a common framework. So this is very useful, for example, if you want to build multilingual parsers. So here's another example, a little bit simpler. In this case, this is essentially a sequential task, part of speech tagging. So here we have a sentence like this: time flies like an arrow, and we want to assign a morphological tag for each word of the sentence. So we want to say that time is a noun, flies is a verb, like is a preposition, and so on and so forth. And so the goal here is to predict this sequence of part of speech tags, which means, because some of the words are ambiguous, means we need to look at the context to see what part of speech tags play well with the neighboring words. So for example, flies, it could be a verb, but it could also be the plural of fly, which is a noun. Okay. The only way of figuring out what's the right part of speech tag for these words is to look at the entire sentence, or at least the words surrounding flies, and try to understand what fits better for this word in this context. Named entity recognition is another task that we can express by assigning a tag for each word of the sentence. So in this case, we are given a sentence and we want to extract named entities from that sentence. So if you have a sentence like this, we want to say that we Elsevier is a person, and we want to say that Leuven is a location. And one way of doing that is by using something called BIO tagging, where we assign a tag with a prefix B, I, or O that says if this is the beginning of an entity, if it's inside an entity, or if it's outside an entity. So for example, here, since this is just the name of a person, the first word gets a tag begin person, and the second one gets an inside person. And here it's an entity just with one word, so it gets a begin location, and everything which is not an entity gets an outside tag. So this can also be useful, for example, for segmentation tasks. So, for example, in Thai, someone told me that word segmentation is a difficult problem. It's a challenging problem because there's no white spaces separating words, which means that a pre-processing step that is needed in many NLP applications is to figuring out where the word boundaries are. And this can be handled by using BIO tagging schemes similar to this one. Okay, so given these examples, let me start establishing some notation that I'm going to use throughout the lecture today. So I'm going to denote the input set by this calligraphic X. So this can be, for example, the set of sentences in a language. I'm going to denote the output set by Y. This could be, for example, the set of part of speech tag sequences for that sentence. And this is the crucial assumption that we are going to make today, and this is kind of what characterizes structure prediction, is that this output set Y is very large and structured. So for example, if we are doing part of speech tagging, and if you have a sentence with a length L, with L words, how many possible outputs exist for that sentence, assuming that we have K possible tags? how many different ways of labeling the entire sequence? Does anybody want to guess? K to the L, right? So it's going to be exponential in L, right? So as the size of the sentence grows, the number of possible sequence labelings is going to grow exponentially fast, which means that we cannot just enumerate all possible labelings, compute a score for all the sequence labelings, and then do the argmax. It's not tractable. It's going to be very expensive. And so today we're going to resort to linear models. So if you like neural networks, you need to wait for tomorrow. But a lot of the things that I'm going to say today, they're also applicable if you have a neural network. And I'm going to explain that later. So basically, I'm going to assume that we have a weight vector that I'm going to denote by W. This is basically a weight for every feature. We have a feature function that is going to take inputs X and outputs Y. So sentences and part-of-speech tag sequences, for example. And it's going to assign some number to this pair. And then I'm going to take the dot product between the weight vector and the feature vector. And this is going to define a linear compatibility function. So this is going to tell me how compatible is this Y to this X. Okay? And the goal is to pick the Y that is the most compatible with X. And so there are two problems that I'm going to talk about. One is the training problem, how to learn the parameters, the weights W from data. So I'm going to assume that we are in a supervised learning paradigm where our training set contains pairs xt, yt. So we have a few examples of sentences together with their part-of-speech tags. And the decoding problem where given a model W that is already trained, how can we, given a new X, a new sentence, how can you predict the Y that maximizes this compatibility score? And of course, because there are exponentially many outputs, this argmax is not trivial. I cannot just enumerate all possible Ys, compute the value of this compatibility function for each of it, and then pick the argmax. We need to be smart about it. So in particular, we need to assume some sort of structure in the model. So this decoding problem, it's also called inference problem. And this is basically what I was saying. So if this was a multi-class classification problem, so if the set calligraphic Y was just a set with a few elements, it will be fine to compute this argmax. So this would not be a problem. But in structure prediction, our crucial assumption is that this argmax is not trivial. And so the key assumption is that the compatibility function is going to decompose into parts. And I'm going to be very vague for now about what these parts mean. This depends on the problem that you're trying to solve. For example, if we are doing sequence labeling, part-of-speech tagging, the scores might factor as a sum over label n-grams. For example, you could have a score for every pair of consecutive part-of-speech tags, and you want to compute the sequence labeling that maximizes the sum of these scores for all these part-of-speech tag bigrams. For example, if you're doing dependency parsing, where we want to predict the dependency tree that connects the words, maybe the scores can be a score for every arc that connects the words, and you want to predict the spanning tree that maximizes the sum of the scores for the arcs. But this really depends on the problem that you are solving. If for example, if we are working on a problem where the output can be expressed as the labeling of a graph, then maybe our parts could be the clicks of the graph. Okay, so this is our roadmap for today. I don't know how much of the left sides we have covered already. So in the basic machine learning classes, did someone talk about naive Bayes? No? What about logistic regression? Yes? I see some faces saying yes. Okay, good. What about perceptron? Good. And SVMs? No. Yes? Okay. So some of these things have been covered, others not. It's not a problem. It's fine. So today what I'm going to do is to kind of show the structure prediction analog of each of these things. All right, so let's start with Markov models. And so the key problem that we want to solve with Markov models, but like the key problem that I want to pose now is, suppose that we have a set of strings, and we want to define a probability distribution over strings. Okay, so strings are a sequence of discrete symbols. Okay, so we can think of strings as, for example, a sentence in a given language. And so why is this challenging? So the challenge is because I'm not specifying like a maximum size of the string. Okay, so if the length of the string is unbounded, this means that there are infinitely many strings. Okay, so we need to have a probability distribution over infinitely many possible values. And we want to make sure that the distribution is going to normalize to 1, because we want it to be a valid probability distribution. And so, of course, if we are defining a probability distribution over finite random variable, doing this normalization is easy, right? You just, we can do a softmax transformation, for example, and in the end divide by all the mass that goes for all the variables, and that's it. But if we are working with a set infinite that contains infinitely many objects, in this case countably many, so it's not continuous, it's still discrete, but there's infinitely many things, there's going to be a few more challenges, and I'm going to kind of slowly talk about possible approaches to this problem. So here's our setup. We assume that we have some alphabet sigma, so we can regard this alphabet, for example, as containing all the words in a vocabulary. So, for example, in English, we can imagine that this set contains like tens of thousands of words. And I'm going to talk about the set of strings that I'm denoting by sigma star, which is called the clean closure of the alphabet sigma. That is basically the union of strings of all sizes, okay, including the empty string. So the empty string, I'm denoting it by epsilon here. So this is the empty string. This is all strings with 1 word. This is all strings with 2 words, and so on and so forth. So this is an infinite set, but it's countable. So there's many elements of this set, as many elements as the number of natural numbers. And we want to define a probability distribution over sigma star. And we want this distribution to normalize properly. So you want the sum for all x belong to sigma star. We want the sum of p of x to be 1. So let me start with some trivial choices that solve the problem. Maybe it's not what we want, but they solve the problem. So the first approach is, okay, let's just give probability 0 to all sequences that are greater than a specified length L. Otherwise uniform. Okay, this is fine. So by doing this trick, we basically got rid of the problem of having infinitely many strings. So now we are the set that has non-zero probability is finite. It's basically all strings with length L, and we're just saying that it's uniform there. So this is not, it's probably not what we want, but it's a valid probability distribution. The second choice is, okay, let's suppose that we have a sample of sequences. So we are given, several sentences in English, and so we're giving n of them. And let's assign a uniform distribution to everything that we observe in that sample, and 0 probability to everything else. So this, of course, will also be a probability distribution over strings, but again, it only has a finite support. So there's only a finite number of strings that gets a non-zero probability, and it doesn't generalize. So if I give you a new sentence that you never observed before, then this model is going to assign 0 probability to that sequence, and this is probably not what we want. So what if we want every sequence to have some probability? What can we do? So one possible approach, and this looks a very naive model, but it's actually widely used in NLP. It works very well for many applications, for example, in information retrieval and so on, is the bag of words assumption. So this is basically saying that the probability of a sequence that goes from x1 to xl, I'm using these 2 delimiters here, start and stop, just to mark when the sequence begins and stops, because this L is not fixed, but we are assuming that the sequence has variable length. So according to this model, we define the probability of a sequence as a product of the individual probabilities for every symbol. So this factorizes completely. So basically what this is saying is that each word is generated completely independently of other words. There's nothing that correlates these words. And so one thing that you might notice by looking at this expression is what happens if I swap two words, if I change the order? Does anything happen? Is the probability different? No, it's going to be the same, right? So I can change the word order, but the probability distribution is going to stay the same. So this is insensitive to the word order, which is something that's, for many applications, it's not something that we want, right? In particular because, language depends a lot on the word order. If I take an English sentence and I swap the words, then I can either change the meaning of the sentence, or I can produce a sentence that is not grammatical. So we want to have a probability distribution that cares about the word order. Okay, so, and how many parameters does this model have? How many? So let's suppose that that you have our vocabulary size is V. Okay, so we have V words in the vocabulary. This has V parameters, right? Because we have a probability for every single word. Right. Okay, so this is like a very simple. It's a lower extreme, like a very simple model. It's not structured prediction because we are assuming that our output variables, our x's, they don't relate to each other. They're all independent. And in structured prediction, usually we assume that there is a dependency between the variables. And now let's go to the upper extreme. So this is the other extreme. Okay, let's assume that the generation of each word depends on the entire history. So we can write that down by writing the probability of the full sequence as the product of the probability of each word xi conditioned on every word that was generated before xi, conditioned on everything on the left. Okay, so this has a huge expressive power. In fact, are we doing any assumption here? Which assumption are we doing by this expression? Are we losing any representation power by assuming that this distribution factorizes this way? No? Yes? We are not. This is just the law of factorization of probabilities, right? So we have all these random variables, and we can write the joint probability of random variables by writing the product of probability of the first words times probability of the second one given the first one times probability of the third one given the two first ones, and so on and so forth. So we are not doing any assumption here. This model is completely generic. It works, for every sequence. Okay, so it has the maximum expressive power that we might reach. But on the other hand, there's too many parameters to estimate. So if we insist in using this model, and we want to estimate all these probability values, how many parameters do we need to estimate?
Does this kind of model limits the ability to look forward?
So in fact, what I'm saying is that you can write, if you start with any form for this probability distribution, we can always express it by assuming a factorization of this kind. Okay, here I'm assuming that this factorization happens in a left-right manner, but if I have a different ordering, I can also use a different ordering and using a different factorization here. But the point I want to make here is that we are not losing any expressive power by doing that. So let's suppose that we start with 3 random variables, A, B, and C. This is just saying that the joint probability of A, B, and C equals the probability of A times the probability of B given A times the probability of C given A and B. So this is just a law of factorization of probabilities, nothing else. Okay, so does anyone want to guess how many parameters you need to estimate if we want to do this? Again, assuming that the vocabulary size is V. No? It's going to be exponential in V, right? Because, sorry, it's going to be V to L, right? Because well, V to L, assuming that we have a maximum L that we want to estimate. In practice, it's an infinite number of parameters, right? Because we're not assuming that L is fixed. So this is completely infeasible. But even if it was feasible, if you could estimate these parameters if you could estimate these parameters with some training data, it will be very hard to make this model generalize because it would require a very large training data set for being able to estimate all these probabilities accurately. But so tomorrow I'm going to come back to this model, not basically the model that tries to estimate each probability value like it is, but I'm going to come back to this model by assuming that there is some continuous vector that represents this conditional probability of a word given all the previous contexts. And I'm going to show that those models perform very well. So this is basically underlying autoregressive models used, for example, in recurrent neural networks. Okay, but let's talk about something in between. So let's suppose that the model doesn't assume that each word is completely independent from the others, and it also doesn't use the full history. So let's suppose that we have a finite memory. In particular, let's start by assuming that each word only depends on the previous word that has been generated. So if we assume that, then the probability of the full sequence can be written as a product of probability of xi given xi minus 1, just the previous word. Okay, so if you do that, how many parameters do we need to estimate? Any guess? V squared, right? Because you need to have a parameter for every pair of words. So you have a quadratic number of parameters. And of course, we need to include the initial probabilities, probability of x1 given start. So there's a linear number of them for every word in the vocabulary. This is basically allowing us to model how likely are we to start a sentence by a particular word. And we also need to model the probability of stop given the last word. This is basically allowing us to capture how common it is to finish a word with finish a sentence with a particular word. So, for example, this probability might be bigger if XL is a punctuation than if XL is a word which is not a punctuation. All right. So, actually, the solution was here. Okay. So, if you don't want to assume that the model depends only on the previous word, but you want to extend the memory of the model a little bit more, then we obtain something called the case order Markov model. So this is basically doing something similar to what I had in the previous slide, but now instead of getting a probability of xi given only xi minus 1, I'm assuming that the context contains a window of k-words. Okay, so this is remembering all the previous k-words. It's still not the full context, it's just a finite window, but by increasing k accordingly, then we can control how much memory this model has. And so if you do that, we need to estimate these transition probabilities. We need to estimate for every word in the vocabulary and every possible context, we need to estimate the probability of a word given that context. And so the total number of parameters, I'm not going to ask because it's already here. The total number of parameters in that case is going to be exponential on k. So as we increase the window of the context, the number of parameters is going to grow exponentially fast with the size of that window. But yeah, so this model is extremely popular in language modeling. And before this research of neural language models, this was the state of the art in language model, even though it's extremely simple. And models like these have been applied very widely to machine translation, speech recognition, optical character recognition, and so on. Okay, so let's assume that we have a case order Markov model. How can we estimate the parameters? How can we estimate these transition probabilities from data? So data here means that we get to observe a set of sequences generated according to the probability distribution that we want to estimate. For example, let's suppose that we have a set of sentences in English, and you want to estimate these k-gram probabilities from those sentences. How can we do that? So the classical technique that is used is maximum likelihood estimation. I'm guessing that we probably covered that in one of the lectures already. And I'm sparing the details here, but if we apply the maximum likelihood estimation criteria to estimate these probabilities from data, then the solution, the ML estimate, is going to be basically boiling down to counting and normalizing. So this means that we need to count how many times we observe each k plus 1 gram, how many times we observe a context, divide the first by the second, and this will give us an estimate of the probability of seeing xi if we observe this context before. Right? So it's very easy to obtain these estimates, right? It's just basically looking at the data, looking at these samples that we have, and counting, normalizing. So we don't need to do any optimization or any fancy technique. You don't need to train any network to learn the model. It's just counting. But there are a few problems. So what if we never observe a particular k-gram at training time? If that happens, what's going to happen at test time? So if you use the maximum likelihood estimation, this means that we are going to assign a probability of 0 to some words. And this, in many cases, this is undesirable. So another way of saying that is that as k grows, as the size of our context grows, the model becomes more expressive. But on the other hand, we're starting to suffer from insufficient data. So we don't have enough data to estimate accurately all the parameters of our model. And so as a consequence, by using these maximum likelihood estimates, we get probabilities of 0. And this is very undesirable. So like a classical example is this language model that is giving probability 0 to unseen words. So just because an event has never been observed in the training data does not mean that it cannot occur in the test data. And so, yeah, so the answer here is basically what we have there. So if the count is 0, then the default answer by using maximum likelihood estimation is that the probability is 0, but you don't want it to be 0. We want to modify the model a little bit. We want to do some regularization, some smoothing, such that we still assign some probability even to events that you never observed in the training data. And I'm not going to talk about smoothing in details because this could take the entire lecture, and it's probably not the best use of time. But I'm just pointing out that there's many smoothing techniques that have been proposed in the literature for decades. So the one that is considered the state of the art right now is the modified Naserney smoothing. But the right way of smoothing is a black art, and there's many heuristics to define the best ways of smoothing. Okay, so Markov models are very simple. Let's see how well they perform. So before seeing these, is there any question about Markov models? Is this completely new to you or very obvious? How many of you already know Markov models before? Okay, a lot of you. And how many of you never saw these before? This is the first time you're looking at this. Half. Okay, so do you find this simple or not? This description of the model. So this is the simplest model that I'm going to describe in all these 3 lectures. The others are going to be a little bit more complicated. Okay, so they're very simple. Let's see how well they perform. This is an example of the outputs. This is sampling from a unigram model. So this is not a Markov model. This is basically the lower extreme that I mentioned in the beginning where we assume that each word gets its own probability and the word order doesn't matter. So this is the bag of words model. And so this is estimated on a corpus of 2.8 million words of political blogs. And this is what happens if I sample each word independently. Okay, so you're not getting anything with good quality, right? This doesn't make any sense. Even though it's kind of it's capturing, so the words that are frequent, like it, and, but, I, and so on, these words are actually occurring multiple times, which is kind of it makes sense because these words are going to get a high probability according to this unigram model. So we are likely to sample more and more words of this kind. So this is sampling a lot of stop words. But other than that, it's not generating anything that looks grammatical. Okay, so let's increase the context size a little bit. So this is a bigram model, a first-order Markov model. So we are conditioning the word that you are generating on the previous words. And if you do that, it gets a lot better. So, for example, the first sentence, for a while, we can even be fooled into thinking that this is a real sentence. The lack of the Senator McCain and keep this story backwards. Well, then it suddenly doesn't make any sense. So it's still very limited. But at least we start off getting things like this, like the lack of the. Okay, so this basically the becomes more likely after off than after a different context. And so this is able to generate short sequences that kind of are plausible in a language. Of course, we can keep increasing the context size, and if you do that, the quality of the sample improves. This is a little bit better than the example before. If you use a 5-gram model, it's much better. You realize it's fully how shallow and insincere conservative behavior has been. Well, then things don't get very grammatical. I know it's very easy to figure out that this text is not real, but still, it's much better quality. It gets locally. It gets it's much more plausible than what we get with the unigram or bigram model. And this was just a teaser. So tomorrow we're going to see more examples of generated text using more recent techniques that are way more impressive than these ones. But this is just to tell you, what we can do with a model that is as simple as something that just counts and normalizes. Okay, so this finishes Markov models. Let's move on to hidden Markov models. So here's what hidden Markov models are. So we are going to assume that instead of each word being generating depending on the previous words, each word is now associated with the hidden states yi. Okay, and we never observe this state. So we are going to consider 2 alphabets now. We still have our word alphabet sigma, but now we have an alphabet for the states that I'm denoting by lambda. And then the generating process is as follows. We are going to generate a sequence of states according to a Markov model. Okay, so not the words, but the states. So we're going to draw states from these alphabets according to Markov model. And then where each state is going to emit a word by conditioning that word on each state. And so, this is a simple model, but there's a wide number of applications. So this has been used in part-of-speech tagging, named entity recognition, word segmentation, and so on. So here's a more formal expression. So we are saying that the probability of a sequence, the joint probability of x and y, where x is the words and y are the states. So the probability of a full sequence factors this way. So there's a probability for the transitions over the states, yi given yi minus 1, the current state is conditioned on the state before. So this is just a Markov model, a simple Markov model. And then we have emissions where each word xi is conditioned on the state yi. These are called emission probabilities. Okay, so we have transition probabilities, a Markov model over the states, and emission probabilities which express the probability of a word given a state. So if you want to draw a graphical model that explains this process, it looks like this. So we have a Markov sequence of states. These are the y's. We don't observe the states. And then each state is going to emit a word, and there is a conditional dependence of a word given the state, and the words are observed. Okay, so what are the parameters in this model? The parameters are going to be the transition probabilities, these ones, and the emission probabilities. And the total number of parameters, I was going to ask this, but it's here already. So the total number of parameters is going to be this quantity. Okay, so this basically means that we need to have this product of the size of the word alphabet and the size of the state alphabet in order to express all the emission probabilities. And then, since we have a first-order Markov model of states, we have a quadratic dependency on the number of states, because we need to express the probability of a state given the previous states. So in practice, if we are applying these for example, words and part-of-speech tags, the number of states is much smaller than the number of words. So this means that this term ends up being a lot bigger than this one. Okay, so let's suppose that we have already an HMM. We have our the estimates of our emission and transition probabilities, and let's assume that you want to use it for sampling a new sequence. Sampling is extremely easy. This is not just for HMMs, but for any directed graphical model. We can use something called ancestor sampling to sample labels from the graphical model. So in the case of HMMs, there are two equivalent ways of sampling. One is, okay, let's sample a full sequence of hidden states using a Markov model. So sampling all the y's, y1 to yl, until we hit the stop symbol. And then for each state, let's sample words by sampling it from the emission probability. Okay, conditioning on the yi that we have sampled already. This is the first way of sampling. The second one is just to alternate between sampling the next state and then sampling the current word from the current state. They're essentially the same thing. Any questions about this? Right. Okay, so we're going to talk about three big problems in HMMs. And these are the three. So let's assume that we get to observe a word sequence, but we don't know the state sequence. Okay, so we observe a sequence that starts with the start symbol, then x1 to xl, and then it stops. This can be a sentence, for example. So we're going to talk about three different problems. One is, given this sequence, compute the most likely sequence of states. Compute the sequence y1 to yl that maximizes the probability of the states, the state sequence, given x. And so, this was one of the first questions that I asked, like how many elements are here in these argmax? There is exponentially many as the length of the sequence increases, right? So it's exponentially many on L. So exponentially on L. The second problem is, given this sequence, compute the probability of that sequence, P of x. And also compute the posterior state probabilities. So this is basically when x is observed, what is the probability for every position and every label, every state at that position? What is the posterior probability of yi given x? Okay. The third problem is, given a training sequence of words and states, so if you have training data, again in a supervised scenario, if you have training data that contains pairs of x and y, how can we learn the model parameters? And we're going to consider also a variant of this problem where our training data doesn't contain the states. It only contains sequence of words. In that case, can we still estimate the model probabilities, and how can we do that? All right, so what we're going to see is that problems 1 and 2, they can be solved with dynamic programming, which is a technique that is widely used in NLP. Therefore, I'm covering it today. And problem number 3 can be solved by just counting and normalizing. Well, at least the problem where we observe both the words and states. So let's look at the first one. And this requires explaining this concept of dynamic programming. Who of you already heard of dynamic programming? Okay, who never heard of dynamic programming before? Okay, most of you did. That's good. So dynamic programming is a key concept that is applicable to many structured prediction problems, and it's applicable in many problems that are not just related to machine learning. So the key idea is to use a table data structure that is able to store partial quantities that we can cache and that we can reuse many times. And so basically to compute the optimal substructure, we're going to look at the best solution to a problem that looks at the best solutions to its similar looking subproblems. So we are going to look at, okay, if we want to compute the best way of reaching this point, what was the so in order to reach this point with this state, what is the best way we could achieve this point? I'm going to give you some concrete examples afterwards. And so there are many examples of dynamic programming algorithms, including the Viterbi algorithm that I'm going to cover today, the algorithm for computing Levenstein distance, also known as edit distance, Dijkstra's shortest path algorithm, Bellman equations, and so on and so forth. Okay, so let's look again at problem 1, computing the most likely state sequence. So in that case, this is the problem that we want to solve. We are given the sequence X that we observe, and we want to compute the sequence Y1 to YL that maximizes the probability of Y given X. And since X is observed, we can write this argmax also as the argmax of the joints of X and Y divided by P of X, but P of X is a constant. So we can just instead of writing the P of Y given X, you can write the joint probability of X and Y. It doesn't change the argmax, and this is going to look like this expression here. So we want to compute the Y's that maximize the probability of the joint sequence of X and Y. Right? So words and states paired together. And now, since we assumed that we have HMM, we can write this expression for the probabilities in this way, where we have a product involving transition probabilities, and we have another product that involves emission probabilities. Okay, and we want to compute this sequence Y1 to YL that maximizes this overall objective function. Does this make sense? Okay, so this is a combinatorial problem, and if you do it naively, then we need to search over exponential number of possibilities, exponential in the length of the sequence. Of course, we don't want to do that. We need to do something smarter. And so, to explain what we're going to do, we need to introduce this concept of the Viterbi Trellis. So let's take again this example that we had in the beginning, the sentence "time flies like an arrow," and let's assume that this sentence, each word of this sentence is ambiguous. It can have more than one part of speech tag. So, for example, time could be a noun or an adjective, flies could be a noun or a verb, like could be a verb or a preposition, and so on and so forth. Of course, there's more than two, but I'm just simplifying and assuming that each word can only have two part of speech tags. And we can represent the problem of finding the best labeling of the sequence as finding the best path through this lattice. Okay, so the actual solution is going to be this one that is highlighted in green. I don't know if you can see the colors very well, but this is basically the path that corresponds to the correct solution. And so the goal of the Viterbi algorithm is going to be determining the path that maximizes the final probability. So the key idea here is using recurrence. So we're going to traverse the sequence left to right and compute the best way of reaching the word at position I, given the possible decisions that have been made in the previous word. And as we do that, we are going to fill a table along the way, and in the end, we are going to backtrack to recover the best sequence of states. So in other words, we're going to compute entries in the table according to this expression. This is the recursive expression. So we're going to store these quantities, v of I, yi. This is basically one number for every position in the sequence and every possible tag or every possible state at that position. And we need to compute this size, which are basically the argmaxes corresponding to this max. And so the interpretation of this is, okay, let's suppose that the best way of reaching the state yi minus 1 at position y minus 1, or the value at that cell, is stored here. Now I want to update for the next position and the state yi, and I do that by basically looking at what is the maximizer, what is the maximum of this expression. So this is basically multiplying the transition probability of transitioning from state yi minus 1 to state yi, emitting the word xi at state yi, and multiplying with the previous entry that I had in the table. And the psi's are just the corresponding to the argmax of that expression. So this is what the Viterbi algorithm looks like. We traverse the sequence left to right. We have a way of initializing the entries in the first position for every possible state. And then for every position, we're going to consider all possible states at that position. And we're going to update the entries in V and updating the back pointers in psi. And then there is a backward pass where we're just going to follow the back pointers to recover the best likely sequence. So I'm going to show you a concrete example that is easier to understand than this algorithm here. So let's take again this example. So we have the sentence, time flies like an arrow. Let's start from the left. So let's look at the position 1 that corresponds to the word time. And let's compute a value for time being a noun. We do that just by multiplying the probability of noun given start. This is our transition probability, the probability of a sentence starting with a noun, and the probability of time given noun. This is the emission probability. And we get this value, 0.04. And you do the same thing for having adjective at position 1. And you get this value 0.01. And we are not going to pick any value, okay? So we are postponing our decisions until the end. So we are not saying that, okay, this is a noun because this has higher probability. We need to keep multiplying these probabilities together to see what's going to happen in the end. So in the second slot, we are going to update, we're going to look at position number 2, where the word flies is, and we are going to compute a value for that position for the state noun, and a value for that position for the state verb. And this is where we need to do some maximization. We need to choose between two things. We need to choose between the previous word, time, being a noun or an adjective. This is where we plug the value that we got from the previous iteration. So in that case, we need to maximize between these two things. Probability of noun given noun times flies given noun, times the value that we have stored in the previous position for noun. This is basically assuming that the previous word time was a noun, and the same thing assuming that the previous word time was an adjective. Okay? And if you do that, we get the maximum of these two quantities. That is basically, it's going to give this value, and the argmax is saying that time should be an adjective. Okay, but this is only assuming I'm only computing the cell for flies being a noun. I need to do the same thing for fly being a verb. And for that example, then it's better to assume that time is a noun. Okay, and this is what we keep putting in the table, and just keep iterating these multiple times until we reach the end of the sequence. This is what happens at position 3 for the word like being verb or preposition. So in that case, for like being verb, it's better for flies being a noun, and for like being a preposition, it's better for flies being a verb. But we still haven't committed to any decision. Same thing for the next position, same thing for the next one. And then at the end, we reach the stop symbol, and we need to choose, okay, what's the best way of stopping? Is it the previous word being a verb or a noun? And the conclusion is that it's better for the previous word being a noun. And this now concludes our decision for for the last word. So we now know that arrow is a noun. It's not a verb. And now we can backtrack by following the back pointers. So now we know that the best way of reaching a noun here is if n is a determiner. We know that the best way of n being a determiner is by like being a preposition, and so on and so forth. So we get the full sequence where time is a noun, flies is a verb, and so on and so forth. Any question about this? So I'm guessing that those of you who have learned already about dynamic programming probably have seen this before. Maybe not in this level of detail, but I think the best way of learning this is actually implementing it. So if you want to kind of have your own experience, I really recommend you to try to implement this. It's very simple. It's probably not going to work at the first attempt, but as you debug it, we are going to learn how these things work. Yes?
In real implementation, do you have to expand the search space here, because it's not gonna be just two paths.
Yes, true.
These two possible.
So
paths,
this
right?
this description was simplifying things a little bit. In practice, you might need to consider all possible part-of-speech tags, like let's say 10 or 15 possible values. But this basically means that instead of having the maximum between two things, you need to do a maximum over more than two. But everything else is the same. So conceptually, it's exactly the same algorithm.
Thank you.
So another thing that I'm not mentioning here, but another thing that in practice, if you actually start implementing this, the first thing that you will note if you implement exactly what I have here is that you're always going to have a probability of 0 in the end. Why is that? This is because you are underflowing. Okay, so we are multiplying a lot of these probabilities together, which means that our final probability is going to get smaller and smaller. If you don't do anything about it, we can already see that, right? So here the final probability is already 10 to the minus 6. And this is going to become worse and worse as the sequence length gets bigger. And so there are several ways of fixing that. One of them is to work on the log domain instead of working on the linear domain. So basically it means working with the logarithms of probabilities and not probabilities, and this fixes the problem. There are other possible ways of fixing it. Okay, so to sum up Viterbi, this is an instance of a dynamic programming algorithm. It's used to compute the most likely sequence of tags. So in other words, the structured output that maximizes the total score probability. This is called the maximum posteriori decoding. So we are just computing like a single solution, the best sequence, the argmax, the best y when x is observed. Later or next, we're going to talk about marginal decoding as a way of computing another output sequence that minimizes the total risk. But first, let's look at the three problems in HMMs, and let's look at the second one. So the second one is, given the sequence x, compute the likelihood, the probability of that sequence, P of x, and compute the posterior state probability of yi given x. So this means what are the probabilities at a particular position of a particular state when the sequence is observed. Okay, so and if you compute these quantities naively, this is what the likelihood looks like. So we need to marginalize out the y's. So we need to have this gigantic sum over all possible labels, sequence labelings, y1 to yl, of the joint probability of x and y. And then the joint probability can be written as these two products again, transitions and emissions. But we have this gigantic sum here, so this is a problem. We cannot naively compute this sum. It contains exponentially many terms. If we want to compute the posterior state probabilities, it's we get something similar, except that this sum doesn't contain the term yi because we are computing the probability of yi given x. So we are marginalizing out all the other states at the other positions. But so both of these quantities involve marginalizing out the hidden states, and they both involve huge summations. So fortunately, we can also solve this problem by dynamic programming, in actually a very similar way as the Viterbi algorithm. So the key idea is we have this sum of products, but if you look at each term in these products, they don't depend on the full sequence. They only depend on a small window. Like for example here, this only depends on the previous y, and this only depends on the current I. And so the key idea is, okay, let's rearrange these terms by interleaving summations with products. And so if you do that, we obtain something called the forward algorithm, where we can use this variable, recursive variable alpha I yi, which plays a similar role as vi yi in the Viterbi algorithm. So the meaning of this variable is it's going to capture a tail of this expression that interleaves sums with products. And then we keep updating the alphas as we move forward in the sequence by reusing the value of alpha in the previous position. So it's very, very similar to the intuition behind the Viterbi algorithm. In fact, the forward algorithm, so the algorithm that allows us to update these alphas, is exactly the same as Viterbi. The only difference is that we are replacing the max with a sum. So if you recall the slides where we had the Viterbi algorithm, all these maximizations, if you replace them by sums, then we get the forward algorithm. And in the end, we are going to get the probability of x. We're going to have the probability of the observed sequence. There's another way of doing this by doing everything that I just said backwards. It gives the same result. It also gives you the likelihoods of the sequence. That is called the backward algorithm. Okay, so, and in fact, this is basically the recursive iteration that is used to update the forward variable. This is the same thing to update the backward variable. This is the backward algorithm. There is an interesting use case that requires using these two, the forward and the backward. This is called the forward-backward algorithm, which is if we want to compute the posterior probabilities, the probability of yi given x. This was one of the problems that we wanted to solve. Given an observed sequence, computes the probability of a given state at a given position condition on that sequence. This can be done by multiplying together the forward and the backward variables. So I'm skipping some mathematical details here. You might want to go back to the slides afterwards. But this is a very intuitive kind of. If you run forward, run backwards, and then multiply these two variables together, then we get this quantity that we're looking for, the posterior probability of states given the observed sequence. And it also works to obtain the posterior probability of two consecutive states, the posterior bigram probabilities. And you can also obtain the likelihoods either by looking at the final value of alpha, the final value of beta, or by taking any position and computing the sum over all states of the product of alpha and beta. So this solves the second problem that we had in HMMs. And this idea of dynamic programming can take us very far. So the Viterbi and forward-backward algorithms that I showed are just two instances of dynamic programming algorithms, but there's many other problems in NLP, for example, parsing with context-free grammars that can be solved with dynamic programming. And so if you apply this for parsing, the version of forward-backwards that is used for context-free grammars is called the inside-outside algorithm. It's essentially the same intuition, but instead of having like a sequence and the left of the sequence and the right side of the sequence, we have a tree. We have kind of the span of a given node, which are everything that is below that node in the tree. And we have the part of the tree that is outside the span of the word. And we can use something very similar to forward-backward called the inside-outside that gives the probability of that span condition on the sentence. There's also similar algorithms that are used in dependency parsing. There's the belief propagation algorithm that is used in generic graphical models. All these are instances of dynamic programming. Okay, so what you just saw is that the forward-backward algorithm allows us to compute posterior marginal probabilities by multiplying together the forward and backward variables. So we can get this quantity for every I, for every state at that position, we can compute this. This is called marginal decoding or marginal inference, by contrast to maxima posteriori decoding, which is what we get with the Viterbi algorithm. But so if we now have a way of computing the probabilities, the posterior probabilities of states for every position, one thing that we can do is let's look at the label yi at that maximizes this probability at every position. Instead of trying to compute the full sequence that is the most probable, which is what the Viterbi algorithm is doing, we can do forward-backward and then go to each position and compute the label that is the most probable for that position, condition on X. This is called minimum risk decoding. Now the question is, does this give the same sequence as the Viterbi decoding or not? What do you think? Is the question clear? So on one side, you have the Viterbi algorithm whose goal is to compute the most likely sequence of states, the full sequence. On the other hand, we have an algorithm that computes this posterior probability for every position I and every state. And now we can look at each state and pick the tag that maximizes this probability. And the question is, are these two things going to give the same solution or not? Who thinks it gives the same solution? Okay. Who thinks it doesn't give the same solution? I think there's slightly more people who think it's not the same solution. So the answer is yes, it's not the same solution. Okay, so these are two different things. And this requires some clarification, right? Why are they different? When should you use one versus the other? So these two strategies are not in general going to give the same label sequence. In practice, sometimes one works better, sometimes the other works better. And interestingly, posterior decoding can, so this technique of, so this last one that I presented, minimum risk decoding. So here I'm calling posterior decoding, but it should be minimum risk decoding. So this can give a label sequence that itself gets zero probability. How can that happen? So suppose that you have a transition that has a very low probability between two states, but the two states are, for some reason, they are very likely for that word. So Viterbi would, if the transition probability is zero, Viterbi would forbid that state sequence, right? It has zero probability in the end. But posterior decoding could allow it. But I think it's easier to explain this difference by motivating each of these approaches by the cost they minimize. So let's imagine the following game. So let's assume that we have an HMM so we have an HMM and we are going to give a new sequence X, and then we need to label this sequence. So we need to compute the sequence of states Y for this sequence. You need to make a prediction. And our prediction is called y hat. Okay, so this is the predicted label sequence. And then this prediction is going to be compared to the true one, y. And then depending on how badly we do, we will need to pay a fine. And our goal is to, pay the smaller fine as possible, right? You don't want to pay a very big fine. So you want to minimize the expected costs. In other words, we want to minimize the risk. What is your best strategy for this game? So our best strategy is going to depend on how the cost is defined. So let me give you two versions of the game. So the first version is an all or nothing cost. So suppose that we have a fixed fine that you need to pay. You need to pay 100 baht if we get the label sequence wrong, which means that y hat different from y high. It doesn't matter how many mistakes we make. If it's not exactly the same sequence, we need to pay this fine. Otherwise, if you get the right sequence, we don't pay anything. Okay, so what should we do in that case? So in that case, we should use the most probable sequence. So you should use the Viterbi algorithm to compute us the most likely sequence of states, because we want to get the entire sequence right. This is our optimal strategy for this game. A second version of the game is the following. Suppose that we pay a fine for every word that you label incorrectly. So we pay 10 baht for every word that you label incorrectly. So this is a little bit more forgiving because it kind of accounts for how many mistakes we make. So if you do one mistake, we pay 10 baht. If you do two mistakes, we pay 20, and so on and so forth. So it's not a all or nothing cost. And it also suggests that you should focus on reasoning about each word without worrying about the coherence of the whole sequence if we want to minimize the fine that we need to pay. So in that case, what you should do is to use the most probable label y high hat for each word, which means that you should do minimum risk decoding. So this is kind of an intuition behind where we should use Viterbi and when we should use minimum risk decoding. Okay, how much time do I still have? 5 minutes. I will wrap up a little bit. Okay, so right, so we saw how to solve these two first problems. Let's look at the third one, how to estimate the model parameters. So there's two cases that are interesting in practice. One is where we have labeled training data, so we have these pairs xi, yi, so we can use supervised learning. And the second case is that even at training time, we don't have any access to the states y. And since I don't have much time, I will focus on the first one, which is not, the answer is not very surprising. Okay, so we want to estimate these model parameters. We can do maximum likelihood estimation. And again, there is a closed form solution for that, which just accounts for counting events and normalizing. So it's very simple to do. You just need to look at the training data, see how many times these two, well, if you do part-of-speech tagging, how often these two part-of-speech tags occur together. From that, we can normalize and estimate the transition probabilities. And you need to count how often a word occurred with a part-of-speech tag. And by normalizing, we can get the emission probabilities. So the unsupervised learning case is a bit more complicated. I think I don't have time to explain it here, so I will skip it. But if you are interested, you can look at the slides. So the standard solution is to use something called the expectation maximization algorithm, or the EM algorithm. Have you? So who knows about? Who has heard about the EM algorithm before? Quite a few. Okay. So the general intuition is alternating between two steps. So one step where we take our estimate of the current model, we take our estimate of the emission and transition probabilities, and we use the forward-backward algorithm to obtain the estimates for the marginal probability of each state at position I and two consecutive states. And we can aggregate these probabilities and consider them as some sort of fractional counts. And then the M step consists on updating the model parameters, updating the emission and transition probabilities. If this was supervised, we will have the full counts, but we can just use the fractional counts that we obtained from the E step instead of using the true counts. If this sounds, very not very intuitive, just take a look at the slides because I don't have time to cover it now. Okay, so here's a quick summary of HMMs. So the representation consists of a directed sequence model. We have a directed graphical model. Our assumptions is that we are doing a Markov assumption on states, and words are conditionally independent given the state. So if you remember conditional independence notions that have been presented in the causality class, this is basically assuming that all the words are conditionally independent given the states. Decoding or inference are given by Viterbi or forward-backward, depending if you are doing map or marginal decoding. And for learning the parameters, we can do maximum likelihood that boils down to counting and normalizing. So this fills the first entry of this table. And now I'm going to quickly look at other options. So conditional random fields have been proposed in the early 2000s to address two drawbacks that HMMs have in practical problems in NLP. So the first drawback is that the assumption that words are conditionally independent is a very strong assumption. There's always some dependency among words that we want to capture. For example, if there is a question mark in the end of the sentence, that information can be very useful to infer the part of speech tags of the other words, because this is going to affect the order of words, at least in English. The second drawback is that the HMM that I presented doesn't have any coarser feature than words. So, for example, it doesn't look at if the word is capitalized, what are the suffixes, and so on. So, in cases where you don't have enough statistical information about each word individually, you may still resort on fine-grained features like these ones to capture some statistical information. And this is something that CRFs can do. So CRFs are, if you think about logistic regression, which I think you learned in the ML basics class, CRFs are basically a structured variant of logistic regression. So it's the equivalent, it's a counterpart of logistic regression to structured prediction. And the factorization that CRFs do is similar to HMMs, but they are globally normalized. So this means that we are going to have some features defined for individual states and the full sentence. So we can have features that look globally at all the words of the sentence, but only one state. And we have features that look at two consecutive states and still the full sentence. And we have weights for all these features. And this is going to give us a score for every particular state at each position and every particular consecutive states. Then we do a softmax transformation. So we exponentiate this sum of scores and we normalize it. And this gives us the conditional probability of a state sequence Y given X. So this is how CRFs define a conditional probability of Y's given X's. By defining these exponential of sums as a product of exponentials, we can think of these scores as potential functions. So we are going to have some unary potentials for every state at each node, and they're going to have pairwise potentials that look at two consecutive states into adjacent positions. And so, of course, we cannot compute these. So the challenge in HMMs is that if we are naive about it, then computing this normalizing factor is very hard, right? So it's again a sum over an exponential number of terms. So fortunately, give you just like the gist of these models. Fortunately, we can still use dynamic programming algorithms for computing that normalizing factor. And in fact, to compute everything that we need to train and to apply a CRF in practice. So everything is boiling down to the Viterbi and forward-backward algorithms. So one thing that distinguishes HMMs from CRFs is this distinction between generative and discriminative models. So in generative models, we model the joint probability of the inputs and the outputs, the joint probability of X and Y. So when you are learning the model parameters, we seek to maximize the joint likelihoods of these two things. So CRFs are an instance of discriminative models where we don't care about the probability of X. We only care about given X, this is given to us, we want to pick the Y that maximizes this probability. And when we do that, and when we train the model to maximize the conditional log likelihood as opposed to the joint likelihood, we say that the model is discriminative. So this is the same distinction that arises in logistic regression versus naive Bayes. And this is the main distinction, one of the big distinctions between HMMs and CRFs. Of course, this also limits us. So for example, sampling from an HMM or computing the likelihood from an HMM is very simple. So sampling is trivial. I explained how to do that. Computing the likelihood, you can do that with dynamic programming, but we cannot compute the probability of X with the CRF because the CRF is not designed for computing the probability of an input. It's designed to, when you are given the inputs, compute the probability of the output Y. But we can still do everything else. We can compute the most likely sequence of states, the posterior state probabilities. So if our goal is to do part-of-speech tagging, we can use the CRF for that. So to learn the parameters, it's a little bit more complicated than an HMM. So in HMMs, if we are given labeled data, if we are in a supervised learning regime, then we just need to count and normalize. But with CRFs, the maximum conditional log likelihood expression boils down to solving this optimization problem. So it doesn't have a closed form solution. But it's a convex optimization problem, which means that there's no local optimum. So this is different, for example, from neural networks, right? Which have a bunch of local optima, but it's generally hard to compute the global optimum. So in the case of CRFs, with a linear model, this is a convex optimization problem. So we can solve it with techniques like stochastic gradient descent or quasi-Newton techniques. All right, so I'm going to skip these details and just jump to the final conclusion for the CRFs. So the representation for CRFs is an undirected sequence model as opposed to a directed graphical model as was the case in HMMs. This means that we are not modeling, so we have potential functions defined on each kind of pairwise labeling of the graph, and then we normalize everything in the end, as opposed to modeling emissions and transition probabilities. The assumption is that we have a Markov assumption on states, and there's no assumption on the words. For decoding and inference, we can use the same tools as we had in HMMs, namely Viterbi and forward-backwards. For learning the parameters, we need to solve an optimization problem, but it's a convex optimization problem, so there's plenty of algorithms to solve it. And these are some concrete examples about how CRFs, how we can design a very simple model for using a CRF for part-of-speech tagging. These are common features that allow us to get accuracies that are around 97% in the Pentry bank, which is close to state of the art. Even now with neural networks, we can get some decimal points on the Pentry bank, but not a lot better. And this is just using simple features like what are bigrams and trigrams of part-of-speech tags that occur, conjunctions between the word and the previous word and two words before, things like does the word have uppercase, does the word have a digit, what are the word prefixes and suffixes, and so on and so forth. So this is kind of the flexibility that CRFs allow that we cannot easily put in a HMM. So an HMM needs to resort just to these kind of things, these kind of features, like a word together with a tag, and these things. Okay, so there's also examples that I could give for named entity recognition. CRFs have also been applied there. so you learn about the perceptron, right? So it's also possible to apply the perceptron for structure prediction. Well, everything is basically the same. So in the perceptron case, this is how it works. So at every step in our algorithm, we're using the current model to make a prediction, y hat. And if this prediction is correct, we don't update the model. Everything is fine. If the prediction is wrong, then we need to update the model by adding the feature vector corresponding to the correct label, sequence labeling, and decreasing the feature vector corresponding to the prediction. But so at the end of the day, this is what we get with the structure perceptron. It's also making a Markov assumption on states, not making any assumption on the words, decoding an inference only requires Viterbi, and to learn the parameters, we just use perceptron updates. So all these dynamic programming algorithms work for all these models. And there's also an analog for support vector machines. But since you didn't learn that for the unstructured case, I don't need to spend a lot of time discussing the generalization here. All right, so so far, all models that I discussed today are structured, but they are always linear. So I didn't talk about nonlinear models today, non-neural networks. But we know that neural networks are more powerful than linear models. There's lots of evidence for that, especially if you have enough data that can be used to train a strong neural network. So the natural question is, can we mix the two? Can we mix a neural network and a CRF, for example? And the answer is yes. This has been done, and it's the current state of the art in NER, or until very recently, it was basically mixing a neural network with the CRF. So if you take everything that I had in these slides, all the dynamic programming part, Viterbi for the background and so on, and if you assume that the scores are not given by a dot product between weights and features, but instead are computing by, let's say, a feed-forward neural network, for example, a shared feed-forward neural network to each element of the sequence, or a BILSTM, then we can just have a CRF output layer that takes these scores and infers the best sequence of labels, or it infers a probability, a log probability for each state at each position of the sequence, and everything still works. So it's just replacing the linear scorer that I presented here by a neural scorer that has a neural network behind it. And that's it. So to conclude, sequences are a common form of structure. Markov models are simple generative models. They are widely used for language modeling. The main limitation of Markov models is finite memory, and this is a topic that are going to come back in the next class. HMMs extend Markov models by mixing hidden and observed variables. It's possible to do map and marginal inference in HMMs by using dynamic programming, Viterbi and forward-backward algorithms. Structure perception and CRFs and structure SVMs are more flexible. They are discriminative models as opposed to generative ones. But the key point is that you can still reuse all this dynamic programming machinery of HMMs to do inference and learning in CRFs and perceptrons. This is it. Thank you very much, and see you tomorrow.
Do you have any questions? We have enough time for about 2 or 3 questions. Okay, don't have.
Recently, I think maybe last year, I'm not sure, I heard about the neural CRF++. So if you have any comments or suggestions, let me hear.
Neural CRF++. Okay, so I don't know exactly what it is, but I think I can guess. So it's probably going to be like a CRF with a neural scorer, just like the thing that I was describing in the end. And I know that CRF++ was a popular software toolkit for CRFs. So I'm guessing maybe it's kind of a software that puts a neural scorer as the backbone scorer instead of features and weights. So the combination of neural networks and CRFs has been quite effective for tasks like named entity recognition, for example, where we have a BILSTM to produce states for every word, and then you have a CRF output layer that produces sequences that take into account the constraints that you have in BIO tagging tasks. Like, for example, you cannot start an entity that is a person and then have an inside label that is a location, for example. And this is something that we can capture easily with the CRF output layer. So yeah, I've seen a few instances of combining neural networks and CRFs. And this is a topic that we're going to come back tomorrow with. I used it for NER, and it was for the data that I was experimenting with, but it was a little bit better, and it kind of avoided the feature engineering step of designing good features. On the other hand, it didn't avoid the engineering that is needed for coming up with a good architecture for the neural networks, all the hyperparameters.